Believe it or not, you're using it right this second. It's an invisible force that's powering the very device you're watching this on, not to mention the lights in your room and, heck, even the money in your wallet. It's called electromagnetic induction, and today we're going to pull back the curtain and see exactly how it works.
All right, so let's kick things off with a question that, well, it sounds almost like magic, right? How can you create electricity with absolutely nothing but simple motion? I mean, no batteries, no plugs, just movement and a magnet. The answer, it turns out, is hiding in plain sight. And it starts with something you probably have in your pocket right now, your credit card. Okay, first up, motion into money. Yep, you heard that right. You see, that little magnetic strip on the back of your credit card? It's packed with these tiny magnetized iron particles. Now, when you swipe that card, what you're really doing is moving that magnetic field right past a sensor in the card reader. And that simple bit of motion, it creates or induces a tiny electrical current that carries all your financial data. Just like that, motion becomes money. But this incredible link between magnetism, motion, and electricity, I mean, it wasn't always common knowledge. To get to the bottom of this, we need to jump in our time machine and head back to the 1830s. This brings us to Faraday's fundamental force. So, the man of the hour is a brilliant scientist named Michael Faraday. Back in 1831, he was the first to really demonstrate this amazing effect. But what's absolutely wild is that just 1 year later, all the way across the world in the United States, another scientist, Joseph Henry, discovered the exact same thing, completely on his own. Talk about a breakthrough. This discovery was literally going to power the future. So what exactly is this thing they discovered? Well, at its core, electromagnetic induction is actually pretty straightforward. All it means is that if you take a conductor, think of a simple copper wire, and you change the magnetic field around it, you create a voltage in that wire. You're basically giving the electrons a little push, getting them to move, and bam, that's an electric current. And here is that exact principle in action. It doesn't get simpler than this. We've just got a magnet and a coil of wire hooked up to a meter. Now, as long as that magnet is sitting perfectly still, nothing, absolutely nothing happens. But watch what happens the second we start moving the magnet. See that? The needle jumps. We just generated electricity from, well, basically nothing but motion. But Faraday didn't just stop there. I mean, he didn't just discover this phenomenon. He figured out the rules that control it. Which brings us to our next section, the 2 rules of induction. Okay, so Faraday's first law is super simple. It's all about one word, change. A magnetic field just sitting there does absolutely nothing. You have to have change. You need motion. No change, no current. Got it? Good. Then there's the second law, and this one is all about speed. The faster you change that magnetic field, the quicker you move that magnet back and forth, the more voltage you're going to generate. So this gives us 2 really simple ways to boost the power. If you want more juice, you can either move the magnet or the wire faster, or you can just add more loops to your coil of wire. It makes sense, right? More loops mean that the magnetic field is interacting with more wire at once, which generates a much stronger current. Okay, but here's where the story gets a really fascinating twist. See, the universe doesn't just hand over this energy for free. There's a catch, a kind of pushback. This is the law of opposition. This is something called Lenz's law. And what it says is that the electric current you just created, well, it goes and generates its own tiny magnetic field. And here's the kicker. That new magnetic field will always push back against or oppose the original change that made it in the first place. It's like nature's way of balancing the books. No free lunches. A really great way to think about this is like electrical inertia. Just like a heavy box resists being pushed across the floor, this new current resists the very change that brought it to life. And it's this fundamental pushback that actually determines which direction the current is going to flow. Okay, so we've been talking about wires, but what happens when this induction thing happens not in a skinny wire, but in a solid chunk of metal? Well, then you get something called eddy currents. They're also known as Foucault's currents. And you can picture them as these swirling circular loops of current flowing around inside the metal, kind of like little whirlpools or eddies in a river. And since these swirling currents have to follow Lenz's law, they generate their own magnetic fields that, you guessed it, oppose the original motion. This creates this incredibly powerful, totally frictionless drag force. And we've actually figured out how to harness this. We use this drag to create these amazingly smooth and silent electromagnetic brakes for things like high-speed trains. So let's just recap for a second. We have these simple, elegant principles. A changing magnetic field creates a current, and that new current pushes back. From that incredibly simple foundation, we have built, well, basically the entire modern world. Let's talk about the world it powers.
Think about this. Pretty much every major power plant on Earth, I don't care if it's hydro, nuclear, or coal, they all work on this exact same principle. They use some kind of energy to spin a turbine, and that turbine spins a massive coil of wire inside a powerful magnetic field. This creates a continuous induced current, and that is the AC, or alternating current, that comes right out of your wall sockets. Induction is also the secret sauce behind every electrical transformer. See, by running that AC current through one coil, we create a constantly changing magnetic field. That field then induces a new current in a second coil that's sitting nearby. And by simply changing how many loops of wire are in each coil, we can easily step up the voltage to send it efficiently over long power lines, and then step it down to a safe level before it ever gets to our homes. It's genius. And really, the applications just go on and on. Those powerful eddy currents we talked about, they're in the brakes on high-speed trains. They're in induction furnaces that can melt solid metal with no flame at all. Metal detectors, they work by inducing eddy currents in that coin you lost in the sand. We even use induction in magnetic flow meters to measure how fast liquids are moving through pipes. It's everywhere. And it all comes back to this one beautiful, elegant idea from Faraday. The amount of voltage you can generate is just about how fast you change the magnetic field and how many turns of wire you've got in your coil. That's it. It's a law so simple, yet it completely unlocked a new era for all of humanity. So, from something as small as swiping a credit card to something as massive as lighting up entire cities, this invisible force is truly everywhere. And it really makes you wonder, doesn't it? We figured this out in the 19th century, and it's powering our 21st century world. As we get even better at understanding and using this fundamental principle of the universe, what will it power next?